So, okay, today we will take up another topic that is exactly. So, what are the uh, effects of applying the reverse bias voltage? So, okay, just observe this picture. So, probably even in the physics lab and all, you might have done the experiments, forward bias in the diode, reverse bias in the diode and all. So, therefore, here is a PN junction. You can see that it is a reverse voltage okay applied here for this particular graph. So both forward bias and reverse bias characteristics are plotted. Okay, so the first quadrant, so this represents the forward bias where your p-type material is connected to positive terminal of the battery, and n-type material is connected to the negative terminal. Okay, so because of the under the forward bias condition, there is a forward current appearing. The main reason for this is, so we have studied in the previous class that under the application of forward bias, the barrier is going to diminish in size. Okay, so barrier will be reduced by an amount Vf. So therefore, the effective voltage that appears across the junction is V0 minus Vf. So because of that, there is a diffusion of majority carriers and we observe the forward current. Okay, so now here our study is regarding the reverse bias and reverse bias breakdown. So what happens inside the junction? Okay, so whenever a reverse biasing is applied, so the condition is shown in this picture. So p-type material connected to minus, whereas n is connected to positive. Okay, so therefore here also current minus I is shown inside the loop. So it means what? Even under the reverse bias condition also, a small amount of current flow is there, that we call it as a reverse saturation current. Okay, so the small current, the amount of this is very small. Okay, and this small current it exists until a critical reverse bias is reached. Okay, so as long as you apply a critical reverse bias voltage, okay, so up to that point you can observe the reverse voltage. Okay, and at that VBR, that is critical reverse bias voltage, the reverse breakdown is going to happen. Okay, so therefore at this particular voltage VBR, which is nothing but critical reverse bias voltage, so what happens exactly is the reverse current through the diode or across a semiconductor junction, it increases very rapidly or very sharply. Okay, there is a large flow, current flow, that is evident from the graph also here. Okay, so until you reach a voltage level VBR, so the magnitude is very less. Magnitude is very less, almost zero. But suddenly, at some critical value, okay, so the magnitude of this reverse current is it is increasing very rapidly, very sharply. So as shown by this graph, it is almost like a 90-degree line only when you consider this V line as a x-axis. Okay, so this critical breakdown voltage, okay, so it introduces an almost right angle looking characteristics. This is called as right angle looking characteristics. Okay, so in most of the diodes. Okay, now this is what is a characteristic feature in the reverse bias condition. And during this VBR, so whatever this high current is flowing, if this is limited by any external circuitry, okay, so then the PN junction can operate safely. So just similar to the reverse bias condition. Okay, so therefore the parameters that are related during reverse bias are, what are those? Reverse saturation current. First of all, reverse voltage VBR. Because of that, you have the reverse saturation current, and then this is a reverse breakdown current. So these are the three important points concerned with the reverse operation of this diode. Okay. So now when this breakdown occurs, so here we are going to study the two types. One is Zener breakdown, other one is the avalanche breakdown. Zener breakdown and avalanche breakdown. So what is this Zener breakdown? So here three pictures are shown. So figure A, okay, it is the band diagram under equilibrium condition. So what is figure A is representing? It's a heavily doped junction at equilibrium it is. So at equilibrium. Okay, now you observe the ECP, EFP, EVP. So these are all the bands towards the p side. So this is a transition region. You can imagine that space charge region here. ECN, EFN and EVN, they are the bands in the N type material. Okay, so this is the P and N. Now as it is a reverse condition, okay, because we are discussing the breakdown will occur in the reverse operating condition. So you can see that the reverse biasing so will make the transition very deep. Okay, so yesterday we had taken that also. See, now this is what is uh, the reverse bias V naught plus VR. Because of the application of VR, uh, the barrier is very strong, okay, so that the width of the space charge region is also enlarged. And because of this, you can observe in the band diagram and just compare with the equilibrium diagram. Okay, so this particular transition is still deeper because along with V naught, this reverse voltage VR is also getting added. Okay, so now due to these characteristics come to this. Okay, so the same picture is taken here. So EFP, EVN, ECP, ECN, and then EVP and the EVN. Okay, so this represents the band levels in the equilibrium conditions. Okay, now in the part B of this picture, okay, so here it is reverse bias with electron tunneling. Okay, so this represents exactly the reverse bias with electron tunneling from p region to n region, because in the p region minority carriers are electrons. Okay, now in the reverse bias, one thing you should remember that here there is no discussion of majority carriers. Okay, so only there is a movement of minority carriers across the junction. So therefore, from p region, you can imagine where electrons are the minority carriers. Okay, so now they are trying to cross the junction and enter into the other region. Now that process is indicated by a word called tunneling. Now this particular picture shows that tunneling. Okay, so this is reverse bias with electron tunneling from p type material to n type material. Okay, and the last picture, it is the VI characteristics under the, of course, both characteristics are shown, forward characteristics as well as the reverse characteristics. Okay, now as shown in this first picture. Okay, so the crossing of bands, there is a crossing of bands due to reverse bias. Okay, so it aligns a large number of empty states on the n side of the conduction band. Okay, on the opposite side of the many filled states of the p side valence band. So that is because of that reverse bias voltage. So definitely there are a lot of changes with respect to energy band diagrams as shown in this. Okay. Now if the barrier that is separating these two bands is very narrow, okay, now you can just compare that with, so this is the separating region. Okay, this is the barrier that separates these two bands. Now here in the first in figure B, you can see that that separating part. Okay, so this is very narrow. Okay, so when this gets very narrow, then the electron tunneling will occur. So now you just compare this picture with the equilibrium condition. Okay, so under the reverse bias effect, so the barrier which is going to separate these two bands, okay, so this is very narrow. Now this is going to facilitate electron tunneling. Okay, now this tunneling of the electrons, so from p side material, p side valence band, of course. Okay, so from where it is happening, from p side valence band to the n side conduction band, to the inside conduction band, it results in what? Reverse saturation current from N to P. Okay, so this is this tunneling effect. This is this tunneling effect which is going to result in the reverse current from N to P region, and this is known as the Zener effect. Okay. And the probability of this particular tunneling, that is how many electrons, what is the probability of the electrons which are tunneling, okay, so from one region to other region, that probability of tunneling depends on what? The width of the narrow barrier d. Okay, so here the small d, it indicates the width of this particular barrier. Now you can say that, okay, So the how many number of electrons are tunneling from p side to n side, it is directly proportional to, okay, the width here d. Okay, so therefore if this d is very narrower, then probability is more, then probability will be. So that's why the probability of the tunneling depends on width of the narrow barrier, which is as shown in figure b. Okay, so now as the bands are crossed here, okay, so e of p, e of n, you can see here in the equilibrium condition, but in the reverse condition they are crossed. Okay, so as there is a crossing of the bands, okay, the tunneling distance d may be too large. So therefore, however, this particular d, it becomes smaller as the reverse bias voltage increases. Okay, so as the reverse bias is still more, then it may get still narrower, okay, and more steeper also at the band edges, at the band edges. So that narrow space, so it will enhance the tunneling process, and because of that, a large reverse current is going to up. So now this effect, that is the tunneling of minority electrons, okay, so from p side to n side under the effect of reverse bias, that is known as Zener effect. Okay, now when if you still keep on increasing this VR, okay, so when a critical level is reached, that is critical voltage level VBR is reached, so then the magnitude of this reverse voltage is going to increase. When this becomes very large, it results in a very large reverse saturation current. Okay, and we say that Zener breakdown has occurred. So that is one kind of breakdown. Then there is one more, which is known as avalanche breakdown. So avalanche means getting multiplied in large numbers. So in avalanche breakdown, okay, so in lightly doped junctions, the breakdown mechanism is characterized by, so what is called as impact ionization. Impact ionization. Okay, so now because of that, there is suddenly a large number of electrons, okay, so which are emerging out of collision, so which are responsible for the breakdown. Okay, so the lattice scattering events result because of the applied reverse voltage, and it further leads to creation of electron hole pairs. Okay, so what is that impact ionization process? So in that there is a lattice scattering which results in the creation of newer electron hole pairs. So what is that? That is, if the electric field E, if the electric field E in the transition region is very large, okay, then an electron entering the p side, see here in this diagram it is shown, uh, an electron entering the p side may be accelerated, okay, it is increased in its speed, may be accelerated with high kinetic energy, okay, and so that it causes ionizing collisions with other lattice. So this is shown in figure A. Okay, so here a single electron is there. Okay, so as it is accelerated, okay, due to impact ionization, okay, it causes collision. So because of collision, okay, so it leads to carrier multiplication. Okay, so now the original electron and generated electron are both swept to the n side, and holes are swept to the p side. Okay, so here in the avalanche breakdown, what happens? One electron, which is under the effect of impact ionization, okay, as well as lattice scattering, it is going to generate newer electron pairs, EHPs. Okay, so you can imagine one electron will generate two electron will generate four. So like that, in multiple numbers, the number of carriers are going to increase. That is called carrier multiplication. So due to continuous collision, there will be a carrier multiplication, and the original electron and generated electrons both are swept. So across, okay, so therefore the degree of this particular multiplication is very high. Okay, if carriers generated within the transition regions also have ionizing collisions with the lattice, so it means the one electron, it is going to generate two electrons after collision. The generated electrons, if they are also colliding with the lattice, then they will also generate newer EHPs. So because of this, so there will be multiple, there is a multiplication of number of carriers. Okay, so therefore the degree of multiplication will keep on increasing. Okay, so within the transmission transition region, so if the newly generated carriers, newly generated electrons, they also undergo the repeated collision. Okay, so that is an incoming electron, it may collide with a lattice and create a new EHP, that is electron hole pair. Okay, so then each of these carriers so has a chance of generating a new one more EHP. Okay, and so on. Okay, so therefore starting with the original electron, okay, the generated electrons, they also have what the chances of generating the newer electrons whenever they undergo collision. So because of this there is a rapid multiplication of the electrons. This is known as avalanche process, and that avalanche process here it is shown. So one electron, okay, so it is in the transition region, due to collision and the scattering events it is going to generate new. Okay, so one electron, once it is generated, a corresponding hole is also generated. Okay, so therefore the figure A, what it represents, it's a band diagram of PN junction in the reverse bias. Okay, it's a band diagram of PN junction under reverse bias only, which shows a primary electron. So this is a primary electron. The primary electron is the one which is gaining the kinetic energy. Okay, and after gaining the kinetic energy in the field of this particular depletion region, it creates a EHP by impact ionization process. Okay, and the figure B. So in the figure B, what is shown, a single ionizing collision by an incoming electron in the depletion region of the junction. Okay, and in figure C, we have primary, secondary, and tertiary collisions. That is, these two pictures shows so how an incoming electron generates a newer EHP, that is a secondary generations, and figure C shows how the primary, secondary, and tertiary collisions. Okay, so because of them you can see that the number of electrons are still increasing. So therefore here what is one particular analysis is done based on the probability of the collision. Okay, so what is that analysis is? So this is called an approximate analysis of avalanche multiplication process. So here we are assuming some notations. Okay, so let us assume that this capital P is, okay, P is nothing but the probability of having a collision within the lattice. It is not that each and every electron must collide. Okay, so an electron may encounter the collision. So obviously, so when uncertainty is there, okay, so there is an uncertainty associated with every electron. So therefore we are going to get the probability concept. So let P be the probability of having a collision. Okay, and let N be the number of electrons. Let N be the number of electrons. So then assume that there will be P into N number of ionizing collisions. Okay, so there will be P into N number of ionizing collisions. So therefore after that particular collision, the primary electron is going to generate secondary electrons. Okay, so therefore after collision the total number of electrons that we are finding is N into 1 plus P. That is, total number of electrons are N into 1 N plus N into P. What is N here? N is nothing but the primary number of electrons, and P is the probability of their collision. Okay, so once the N number of electrons collide, then the total number of electrons are so N times of 1 plus P, or N plus N into P. Now these whatever secondary electrons are there, okay, so these N into P, okay, N into P it's a product term, N into P pairs, they are again going to generate NP square tertiary pairs. Okay, so therefore the total number of electrons after a series of collision, okay, so this we are going to get as a multiplicative term, that is total number of electrons represented by N out. Okay, so N out is equal to N into 1 plus P square plus, okay, so it continues. Okay. So therefore if you take the ratio N out by N is equal to 1 plus P square plus, it is just like a series, that is equal to, it is indicated as a M M. Mn. So where Mn represents electron multiplication. Electron multiplication. Okay. So therefore, physically, the measurement of this carrier multiplication capital M in the junctions near the breakdown, it is given by a relation M is equal to 1 divided by 1 minus V by VBR. V by VBR raised to N. So now this is a relation. Okay, so near the breakdown region, okay, it gives a measure of the carrier multiplication. So, the total, the capital letter M here is taken as a measure. So that is a function of applied voltage, reverse bias, as well as N. Here N varies from 3 to 6 depending on the type of material used for the junction. So in the problems and all, if any N value particularly it is mentioned, then it can be considered for the calculation. So this particular equations, it gives, so how the number of carriers are getting multiplied due to series of collision. Okay, and that particular operation, that particular phenomena observed at the junctions is called as avalanche breakdown. So because of this, a huge number of carriers emerged out at a time, and it leads to further breakdown of the junction, and which results in a large reverse saturation current. Okay. So these are the two small topics related to the reverse breakdown.